Welcome to The Explainer. Today, we're going to pull back the curtain on one of the most powerful and, let's be honest, complex technologies out there, the nuclear reactor. We're going to explore just how we safely harness all that incredible energy locked inside the atom. So, how do you safely harness the power of a single atom to light up an entire city? Well, it's this amazing blend of physics, some really clever engineering, and an absolutely uncompromising focus on safety. Let's walk through the whole thing together, right from the fuel itself to the final layers of protection that make it all possible. All right, here's our game plan. We'll start with how we get the power from the atom, then see how the reactor works and how that becomes the electricity you use every day. After that, we'll really dive deep into all the safety layers, from the physical walls to the ultimate backup systems.
Okay, so everything, and I mean everything, starts with a process that's, well, it's both really straightforward in concept and just incredibly powerful in practice. And that process is nuclear fission. This is the key reaction, the one that unlocks all that energy we're looking for.
The best way to think about it is like a microscopic chain of dominoes. See, you have a neutron that comes along and strikes a uranium atom, and that causes it to split. Now, when it splits, it releases a huge amount of heat. But, and this is the crucial part, it also releases more neutrons. And what do those neutrons do? You guessed it. They go on to split other atoms, creating this self-sustaining chain reaction that gives us a continuous, absolutely immense flow of heat.
But you can't just dig uranium out of the ground and toss it in a reactor. It has to be prepared really carefully. It starts with mining the ore, which then gets processed into this concentrate called yellowcake. From there, it's converted into a gas, and then it goes through enrichment. Now, all that means is we're just increasing the percentage of the specific type of uranium we need for fission. That's U-235. And once that's done, this enriched material is formed into these small, tough ceramic pellets. They get stacked into long fuel rods, which are then bundled together, and that is what's finally ready for the reactor core.
Okay, so now we have our fuel, and we have a way to make a ton of heat. Let's move to the heart of the plant, the reactor itself. We're going to focus on the most common design you'll find around the world, which is the pressurized water reactor, or PWR, and it has this really clever design feature that is just central to its safety. And this right here, this diagram shows the brilliant core idea of a PWR. If you look closely, you can see there are actually 3 separate water circuits. But the most important thing to notice is the separation between that primary loop, the one in red, and the secondary loop, in blue. See, the primary loop gets superheated by the reactor core, which, yes, makes it radioactive. It then transfers all that heat over to the secondary loop. But, and this is the key, the water from the 2 loops never actually mixes. That separation is an absolutely critical safety feature. Now, while the PWR is the most common design, it's not the only one. There's another type called a boiling water reactor, or BWR. And as you can see, it's a much more direct system. It literally boils water right inside the reactor core, and then that steam goes straight to the turbine. On one hand, that means fewer big components, which is simpler. But on the other hand, it means the steam that's spinning the turbine is actually radioactive. It's a classic engineering trade-off, really. Simplicity versus an extra layer of containment.
Okay, so we've got our high-pressure steam, safely created in that secondary loop of our PWR. But how does that turn into the electricity that lights up our homes? Well, this next part of the process is actually surprisingly familiar. From this point on, a nuclear plant works pretty much like any other thermal power plant, whether it's coal or natural gas. You use the immense pressure from all that steam to spin a massive turbine. That turbine is hooked up to a generator, and as that generator spins, it produces electricity. Simple as that. Then it's sent out to the grid for all of us to use.
And I'm sure you're wondering about that iconic tower, right? A lot of people think that's a smokestack, but it's not. It's a cooling tower. See, after the steam has done its job spinning the turbine, it needs to be cooled back down into water so it can be used all over again. And that is the tower's only job. That big cloud you see coming out of the top, it's just clean water vapor. All right, we're generating an unbelievable amount of power here. So as you can imagine, safety is absolutely paramount. And it's not an afterthought. It's engineered into the very bones of the plant using this multi-layered philosophy called defense in depth. And the whole idea is to create multiple, totally independent lines of defense. I love this analogy. Think of it like a Russian nesting doll, or maybe even a thermos flask on steroids. It's not about having one single super strong wall. Instead, it's a series of robust, independent physical barriers.
and each one is designed to keep all the radioactive materials safely contained no matter what, even in the absolute worst-case scenario.
So let's peel back these nested layers, kind of like an onion. The very first barrier is the fuel cladding itself. These are strong metal tubes that seal in those little ceramic fuel pellets. Okay, so that's layer 1. Those fuel rods are then all placed inside a massive, thick-walled steel reactor vessel, layer 2. And finally, that entire reactor is enclosed in the containment building, an incredibly strong structure made of reinforced concrete and steel that's designed to withstand some pretty extreme events.
But the safety engineering doesn't just stop with a bunch of strong walls. Oh no. Beyond those physical barriers, there's an entire network of systems, some active, some passive, that are standing by, ready to respond automatically in an emergency. These are all known collectively as the Emergency Core Cooling Systems, or ECCS for short. And these systems have one job, and one job only. It's a simple mission, but it's absolutely critical. Make sure the reactor core always stays cool and covered with water, even if the main cooling system were to fail. Their entire reason for existing is just to prevent that fuel from ever overheating. What's so brilliant about the ECCS is that it's a mix of passive and active safety. Let me explain. The passive systems are beautifully simple. They're just big tanks of borated water that are kept under pressure. If the pressure inside the main reactor ever drops, physics just takes over. Valves open automatically and these tanks flood the core. No power needed, no human has to push a button. And that boron in the water, that helps shut down the chain reaction too. Then, backing that up, you have multiple sets of powerful, redundant pumps that can actively inject even more cooling water. Now, what's really remarkable is how the ECCS response is tailored to the specific problem it's facing. It's not a one-size-fits-all solution. For instance, if there's a large, sudden break, the system basically throws everything it has at the problem all at once. You get the passive accumulators firing and all the active pumps kicking in to reflood the core as fast as possible. But for a smaller, more gradual leak, it's a much more measured, sequential response. It'll start with the high-pressure pumps and then bring in other systems only as they're needed. It's just an incredibly intelligent and layered defense.
Okay, let's bring all these pieces together and look at the complete picture of modern nuclear power. When you step back, you see it's really a story of harnessing an almost unbelievable amount of energy through equally incredible feats of engineering and safety design.
So if there's one key takeaway, it's this. Nuclear energy isn't just about making power, it's about managing that immense power with meticulous, overlapping layers of safety. You've got the physical barriers, right? The cladding, the vessel, the containment building. You've got the redundant cooling systems, both passive and active. And you even have the inherent physics of the reactor working for you. A really cool feature of these reactors is that as they get hotter, the nuclear reaction naturally slows itself down. It's a built-in, self-regulating safety feature. Every single aspect of the design is built on this foundation of safety.
And all of this leaves us with a final, important question to think about. We've walked through the process, we've peeled back the many, many layers of protection. Knowing just how much remarkable engineering goes into every level of these plants, well, that's really the essential first step. It's what allows us to have a truly informed conversation about the role this powerful, complex, and clean technology should play in our shared energy future.